Today we have this 90 minutes devoted to a really hot topic in contemporary science, that is researching exoplanets, extrasolar planets. The main invitation came this spring from the organizers that please, Laszlo, organize a thematic session or submit an application for organizing a session, because you can have almost guaranteed access or success rate, or expected success. We did it. In the last 2 days, we have held a workshop on this topic for a more professional audience, for astronomers. And today, the idea is to present where we are right now and where we are heading to in the coming decades in this very field, which got the half of the Nobel Prize in Physics this year, if you remember. I don't want to talk about that, but let me introduce our highly esteemed guests from left to right, which is probably not too polite, so from right to left. Giovanna Tinetti on the right, who is the primary investigator of the European Space Agency mission Ariel, which is to fly in 9 years from now. Please welcome Giovanna. Yep. Next to her is Szilárd Csizmadia, who is a colleague from the German Deutsche Luft, whatever, DLR in Berlin, representing ESA space mission Plato, which is to fly in 2026, from 7 years from now. Szilárd, please welcome Dr. Csizmadia. Second from left is Dr. Christopher Bröck, who is the project manager of the European Space Agency space mission CHEOPS, which is to fly next month. So hopefully that is much closer to us right now than the other two. And please also welcome Jack Lissauer from the United States, who is representing the Kepler space telescope. Please claps for both gentlemen, Chris and Jack. So the idea is to have this very specific, very focused thematic session, not just exoplanets, but organized around the topic of exoplanetary space telescopes. Why on earth we are spending hundreds of millions of dollars or euros, wherever you are on whichever side of the Atlantic Ocean you are hosted, for these missions. And hopefully there are some policymakers in the room, or decision makers, or assistants to policymakers who will grasp the importance of this very field. So the organization of today's thematic session is the following. We have the speakers, the list of speakers. I will be the technician who is changing the presentations. The 4 presentations, each 20 minutes in total, will be followed by an opportunity of discussing the topics and also raising questions from the audience. So please, if you have any question during the thematic session, keep it to the end after the 4 speeches. The order will be by time, so Kepler, CHEOPS, Plato, and Ariel, from 2009 to 2028, which is essentially two decades of exoplanet research. And the topic of the final discussion will be actually sort of a vision, Exoplanet Vision 2050. Where are we heading to in the coming 30 years of time? So with this introduction, I will give the floor to Jack Lissauer from the United States, who is going to present the Kepler Space Telescope, which is certainly something which revolutionized the field. Please, Jack, the floor is yours, so just use the arrows and speak in the mic. I will give the 5 minutes.
Thank you, Laszlo. It's my pleasure to be here speaking to you, and especially my pleasure to be telling you about the results of NASA's Kepler mission, which has found most of the planets known to humanity. Because you're not all experts in planets, I wanted to show this slide as somewhat of an introduction. It's the planets in our solar system in quasi-3D representations. And I like to show this version of a comparison between the planets because it shows two special things. One is that the giant planets are really much, much larger than the terrestrial planets. So all four giant planets in our solar system, much larger than Earth and the smaller bodies of the inner solar system. And it shows that there are three types of planets in our solar system. The inner terrestrial planets are all rocky. They're made up primarily of elements heavier than helium. The gas giants, Jupiter and Saturn, are made up of dominantly hydrogen and helium, the two gases that make up most of the sun also. And then you have the intermediate bodies, Uranus and Neptune, which are dominantly heavier elements by mass, but hydrogen and helium by volume. Most of the planets known around other stars prior to Kepler were gas giants like Jupiter and Saturn. Most of the planets found by Kepler were these small rocky planets and these intermediate planets, most of whose mass is made up of rock-forming elements. Now, the giant planets are huge compared to the terrestrial planets, but they're small compared to most stars like the sun. And not only are they much smaller, they're much fainter. And that's why exoplanets are so difficult to detect. Exoplanets just means planets around stars other than the sun, and why the detection of the first planets around a star other than the sun was awarded the Nobel Prize in Physics this year. Kepler was launched primarily to detect small planets, find out how many planets are out there, not by observing the entire galaxy, but by taking a sample and determining the occurrence rates of terrestrial planets in and near the habitable zone, the region at the right distance from stars such that liquid water could exist on the surface of a planet that has a thin atmosphere similar to Earth's atmosphere. There were several other goals. I don't have time to go into them, but that's the primary one. Now, here you see what's going on. A transit is just a partial eclipse. And above, you see a brown planet transiting in front of a yellow star. Below, you're seeing a measurement of the amount of light from that yellow star that makes it to our telescope, which drops when the planet is in front. We don't see the disk of the star. All we see is the brightness of the star. We measure that, and that's how we get the planets. The brightness drops proportionally to the difference in areas of the two bodies. And for a sun-like star, Jupiter blocks about 1% of the light. That can be detected from telescopes on the ground, but an Earth-sized planet only blocks less than 1% of 1%, 80 parts per million of the light. And because the atmosphere is variable, it's really difficult to get that from the ground. That's why we went to space. Now, transits can only be detected if we are near the plane of the planet's orbit. Indeed, only 1 in 200 randomly placed observers detects the transit of Earth in front of the sun. And therefore, we needed to look at a very large number of stars. We looked at over 150,000 stars. We measured their brightness, added up over 30-minute intervals for 4 years. We looked at the same stars. We measured their brightness every 30 minutes. Well, we had to turn the spacecraft away a little bit, so 90% of the time, every 30 minutes. And we got a precision of the variations down to 30 parts per million when we added the data over 6 hours, which is the typical duration of a transit. We looked at a star field a little bit above the galactic plane, such that we had a lot of stars, but not too many. Not too many such that they would be interfering with each other. I show here on the left a view of the Kepler spacecraft as it was being assembled in Boulder, Colorado. And on the right, the focal plane where we got the image. That is a group of CCDs, and CCDs are the same thing that measures the light in a digital camera or the phones that many of you are using to take pictures during this session. Engineer for scale. These are examples of 5 early planets discovered by Kepler. This shows the variation in light from the star during transits, added up over many transits. We see that all of them have very short period orbits. So we can get a lot of transits, so we can get them very early. They're deep because 4 of the 5 are bigger than Jupiter. Kepler 4b was only about Neptune size. This is our set of planet candidates today, plotted on a radius of the planet in units of Earth's radius. So the top line, top dashed line, horizontal line, is Jupiter radius. Next one is a Neptune radius, then an Earth radius, and the lowest one is a Mars radius. And we see that at very short periods, we detect planets smaller than Mars. At longer periods, we only detect larger planets. That's not because smaller planets don't exist, but because to detect them, we need many transits, and we didn't have enough time. This plot also shows you the number of planets in each system, number of transiting planets, and with different symbols, and it indicates that almost half of the planets are in systems where more than one planet candidate was found. That means the systems must be very flat. Just like our solar system, the planets orbit in nearly the same plane. Now, I mentioned this as planet candidates. The problem is you can get a series of dips, periodic dips, in the light from a star, not only from a transiting planet, but from an eclipsing binary star system. And these are called false positives. They're confusing, and that's why, while we have almost 5,000 exoplanet candidates discovered by Kepler, only about half of them have been verified as true bona fide exoplanets. 80 to 90% of the rest are going to be planets, but we still are in the process of verifying. And this plot shows you a diagram, again, of planet radius versus orbital period. Here we show Kepler planets in yellow, other planets around other stars found by other telescopes in blue and purple. And then there's that lonely ball towards the lower right, which is Earth. 70% of the known planets, more than 2/3, were discovered by the Kepler spacecraft. And if you just looked at small planets, Kepler has been even more dominant. But no planets around other stars like Earth have been found to date by anyone. This is a representation of the first few dozen planets found by Kepler. They're just balls of various sizes, proportional to the size of the planet. A few are bigger than Jupiter, but most are smaller than Neptune. One at this point was even smaller than Earth. And these were the first verified Kepler planetary discoveries. They're not that much to look at. They're just balls of fairly arbitrary color. What you may very well have seen pictures of exoplanets like these. Now, we have wonderful pictures this good of some of the planets and moons in the rest of our solar system, but none of exoplanets. These are all artist concepts. They're science fiction. And those of you who read science fiction are aware that there's hard science fiction that has a lot of science in it, and soft science fiction, which has a little bit of science and a lot of fiction. And most of these exoplanet diagrams are soft science fiction. But I'm going to show you a few that are harder science fiction. They have a little better justifications behind them. And this one represents Kepler's first rocky planet, Kepler 10b. It's about 40% larger than the Earth in radius, and almost between 4 and 5 times the mass of the Earth, which means it's made probably of material, very similar combination of rocky material as in Earth. A little bigger, but its orbital period is less than a day. It's really, really hot. And just like the moon always faces one hemisphere towards Earth, being that close to its star, it probably faces the same hemisphere towards the star, and that area would be really hot and glowing, as in this diagram. Kepler 11 has 6 planets that have been observed to transit in front of their star. This diagram has more science in it than almost any other exoplanet art around, because we know a fair amount about the system. Kepler 11 is a sun-like star, and that's a picture of the sun. The 3 planets seen in transit are in the right position relative to the center of the star, above and below the plane, the right position along the orbit for a particular time at which Kepler observed. And the size ratios of all 6 of the planets, the 3 transiting and the 3 not transiting, are correct. Now, there's also some artistic license. That beautiful nebula in the background, artistic. The picture of the sun is when it was most active and most spotty. Looked better. Those 3 planets not in transit, they've been moved much closer to the star, because 2 of them would not only be much farther than this picture, but they would be outside of this room, and one outside of this building, indeed. And if you wanted to show them at the right positions, you'd hardly see the star, and certainly not the planets transiting. And also, the planet sizes are correct relative to one another, but they've been enlarged by almost a factor of 3 relative to the star. This is what they look like at the correct sizes. Not too artistic. Here we see the data behind it. the transits of all 6 planets, different depths, different periodicities, different durations, and over at about 95 days, you see the triple transit of these 3 bodies. The system is shown here on the same scale as the inner part of our solar system. 5 planets orbit closer to the star Kepler-11 than any planet in our solar system, and the 6th one would orbit between the 2 innermost planets in our solar system. And these planets aren't huge, but they're all at least about 70% larger in radius than our Earth. And all of them have some gassy envelopes, but nothing like Jupiter and Saturn, nowhere near that big. Kepler has seen a few planets in the habitable zone where liquid water could exist on their surface, but they're around much smaller stars. Only large planets around Earth-like, sun-like stars, small planets around small stars. This diagram, if I can get it to play, shows you the orbits of the planets. These are multi-planet systems discovered by Kepler in the first few years, and this shows the actual relative rates of motion and the relative sizes of the planets in hundreds of different planetary systems. All these systems are nearly flat, otherwise we would not have detected multiple planets. So, summarizing Kepler's major findings, planets, especially small ones, smaller than Uranus and Neptune, are quite common. Many, if not most, planetary systems are very flat, like the solar system, and planets and planetary systems are extremely diverse. So we've seen a wide range of planets. We've seen even small planets in the habitable zone, but they're not the same as the Earth and the Sun. No exoplanets similar to Earth in size, distance, and type of star they orbit have been found. It's fairly distant, actually, in at least one of those quantities. And that brings me to a topic, the central topic of this forum, ethical science. We only have one Earth. It's possible that there are other planets like Earth out there, but even if there are very similar, they're very far away. We can't do a migration. We can't solve our problem the way the Irish did in the late 1840s with emigrating to solve the potato famine. We would be like Easter Island. If we don't take care of this planet, we are toast. All the mass extinctions in the past 500 million years on Earth are coincident with substantial increases in carbon dioxide in the atmosphere of our planet. We must stop this crazy behavior. And as scientists who understand if you put more of a gas that allows the visible rays of the sun in and blocks the rays, many of the rays, thermal radiation from Earth from escaping, we're going to make the planet hotter. We've already started this, but we're doing worse and worse. We as scientists who understand that need to lead by example. We can't just say something should be done. We have to do things ourselves. We have to cut our carbon footprints. And if you're like me, most of your carbon footprint is like airplane travel. We want to meet. Conferences like this are very important to science. But going across the thousands of kilometers for a 1 or 2 day meeting, we need to stop that. Going thousands of kilometers in order to give one single talk, we need to stop that. People who organize panel reviews, other discussions, have them less frequently in person, and in the interim, meet by teleconference. If you're doing colloquia for your university or your institute, find other institutes or universities in your area with whom you can share speakers. You can get as many talks as many good people. It'll cost you less. It's just that you have to do a little more work if you're organizing these panels or these colloquia. But we have the responsibility to protect our planet as scientists who understand what is going to happen if we don't act. Thank you very much for your attention.
Thank you very much. I really understand the message. And as the one who was responsible for this organization, I'm more than happy to skip organizing work like this in future times. So I would be absolutely thrilled to end up organizing these kind of events. I will transmit the message, if someone didn't know it. In the meantime, we are here, so let's take the opportunity to move forward with the next talk, which is about a space mission in which we are very proud of the Hungarian contribution locally because of the industrial partners. All sorts of new things happened. And it is really exciting because next month something is going to happen. Dr. Christopher Brögg from University of Bern is talking about the Cheops space mission. Thank you.
Yeah, thank you, Laszlo, for the introduction, and thank you for inviting me to present Cheops. It's an exciting time for exoplanet science, and I'm trying to give you a bit of an insight on the excitement and on the past, and of course for Cheops, the present and the near future. Exoplanets are a story of measurement accuracy. Just 24 years ago, we only knew the planets in our solar system, and simply because it was too difficult to find planets around other stars. As you've heard in the previous talk, it's very difficult to actually measure and detect planets because they're not self-luminous, so you have to use other means to find them. And the two most successful ones is measuring the velocity of the star, so the wobble of the star caused by the planet, or the change in brightness like Kepler and Cheops are doing. And it's a story of ever-increasing precision on these measurements that allows us to make such progress. And as was already stated, this year, almost 25 years after the first exoplanet was discovered, this was honored with the Nobel Prize. It goes in equal parts to James Peebles and Michel Mayor and Didier Queloz, and because they all have transformed our ideas about the cosmos. While James Peebles' theoretical discoveries contributed to our understanding of how the universe evolved at the Big Bang, Didier and Michel explored our cosmic neighborhood, and they changed forever our conception of the world. That's how they saw it, and it's also how I see it. It's a bit like the Copernican revolution, where humanity realized we are not in the center of the universe. It's another step. There are many planets out there, even so maybe they are not useful for us, so we cannot use it as an excuse to destroy our planet, but we are not special, probably. There are probably many Earth-like planets in this huge universe, so we shouldn't take ourselves too important. And so I just want to say one slide here on the Nobel Prize, because it's a different technique than Cheops is using, but it was a radial velocity technique. And if you look in the 80s, you could measure the speed of a star with 1 kilometer per second. That was sufficient to measure a binary star, but it was not sufficient to measure a giant planet around a star. And that was a great achievement of these two people and their team. With LOD, they measured to 10 meters per second. That's how you ride your bicycle if you go really fast, but you must see light years away the star you can measure to this precision. And now they've improved the technique with HARPS and espresso down to centimeters per second, to a slow walk. And then just to tell you what this means, 1 meter per second means you can locate the spectral line on your detector in the laboratory to the position of 150 silicon atoms. And this has to be stable over years if you want to measure on Earth. So that's really a technical challenge they met, and for which then they were awarded the Nobel Prize. So if you look in the past, now we know more than 4,000 exoplanets dated this year. 1995 was the first one discovered around a solar-type star. And then 2002, the first transiting exoplanet was discovered. And then there are other techniques I will not talk about a few years later. And then Kepler launched in 2009, and you see here the pink bars are Kepler. So Kepler made a huge progress in this field of exoplanet, in particular when it comes to statistically knowing what we can expect from exoplanetary systems. Like, is our solar system typical? What's a typical planetary system? And so after nearly 25 years, we know that planets and planetary systems are extremely diverse. It seems like our solar system is not the rule. To me, it's not clear it's the exception, but certainly it's not the rule. We know that planets are common objects, and we know that Earth-sized planets are very, very common. Almost every star has a planet, and there are billions and trillions of stars in the galaxy alone, so there are billions and trillions of planets. So with this I come to CHEOPS. So CHEOPS is the first ESA small mission, a mission conceived that a small consortium and also small countries can take a greater lead in a mission that's usually reserved for the big countries. It's a single telescope of 33 centimeter diameter. It's only 300 kilogram, and the total size is about 2 by 2 by 2 meters. If you compare it to the Kepler spacecraft, it's relatively small. And it was selected in 2012, but already in 2008, Willy Benz, the PI of CHEOPS, and Didier Queloz, the science team chair, had an idea of such a mission, and we were doing a feasibility study on how we could do this. So here, before I come a bit on the overall design, you see the final outcome. That's the instrument in our laboratory on the top left, in the clean room just before shipping to Airbus. It's a telescope. And on the bottom, you see it's being integrated in Madrid. So this happened in the last 2 years. So CHEOPS is a space photometer to improve measurements of the size of selected exoplanets. So we're using this transit technique. We want to measure this dip in the light curve. And this transit is a known thing in our solar system. There's the Venus transit we can observe because the Venus is closer than us to the sun. You can see it on the left. It makes a 75 parts per million effect. And if you look on the right, there's also a small dot. If I enlarge it, that would be Mercury. It's this small. It makes only a 12 parts per million effect on a star the size of our sun. So that's a challenge. And so the CHEOPS mission aims to detect transits of super Earth-sized planets, so about the size of the Earth, around bright stars with 10% accuracy. So we want to reach 20 parts per million. And for Neptune-sized planets, we want to go down to fainter objects and measure them to 2% accuracy. And just to tell you what are 20 parts per million, I put here 1 million points. And if you zoom in and you look at 20 points, that's 20 parts per million. And this you have to measure stably over however long your observation is. If you want to find an Earth, you want to observe for 3 years or 5 years like Kepler did, it has to be stable for these 5 years, otherwise it's probably not going to work. As a minimum, it has to be stable for the duration of a transit, which is typically several hours or days, if you want to measure before and after. So that's a serious challenge. It's a challenge that has been met by Kepler. They reached with all the additional noises also from the stars. They reached 30 ppm. I think they did better on some targets, worse on other targets. So we want to do 20 ppm on the good targets, so we want to be as good as Kepler. And to measure this, we also built a super stable source to simulate this in the lab, because it's not easy to build a lamp that's so stable. And this was also shared with a test team to calibrate the space mission. Organization of CHEOPS is a joint mission between ESA and Switzerland. ESA is the launching state, platform procurement, launch services, and they also provided the detector and the space debris service. And then on the consortium side, we are responsible for the payload, the science operation, and the mission operations center. It's a consortium of 11 countries that contribute. And the total cost is roughly 100 million euros, so it's a cheap mission for a space mission. And ESA is covering roughly half of the cost. And we are proud to say that we are within budget and within schedule. Schedule meaning that we are reaching the first launch opportunity that we could catch, which should launch in 3 weeks from now. If you look at this fleet of space missions, here on the top you see dedicated missions to exoplanet science. So the first one is Koro. It was the first transit find mission, and also astroseismology mission. And Kepler, I think, certainly the biggest success. And now TESS is flying, and then comes CHEOPS. And we are different from the predecessors. First of all, we are much smaller, especially than Kepler, but we're doing it the other way around. We're not a transit search mission, we are a follow-up mission. So we are complementary, that we want to step and stare at single targets that we already know that host planets to get more precision, to follow up later again, and so on. On the science, our science is defined by the CHEOPS science team, chaired by Didier, and the main themes are put here. So we want to improve the knowledge of the composition and structure. So you know, for the Earth, we know pretty accurately how the structure is done. For the exoplanets, usually we just have the radius and the mass if we have bright objects, so we can infer from the density how the planets are, what the planets are made of. We also want to study atmospheres through phase curves, hopefully find moons or rings on planets, and with TTVs discover more masses or other planets in the system. We also have a collaboration with TESS to follow up on interesting TESS targets. And one major goal, of course, is to find golden targets for large space or ground observatories like the Webb or the ELT. And then there's also 20% open time for scientists who want a super stable photometer in space for any kind of science. So just one word on the TESS synergy. So targets are everywhere. So exoplanets are everywhere on the sky. We want to look at bright stars, same as TESS. TESS is focusing on the continuous viewing zone on the James Webb Telescope. So they're focusing on the galactic poles. In the ecliptic, they have less coverage. On CHEOPS, we'll do follow-up, but we can observe best in the ecliptic. So we can observe best where the coverage of TESS is the smallest. So where, for instance, TESS has only 27 days of coverage, we can follow up the targets, and I'm sure many targets will come from TESS. So we are complementary in the science goals, but also in the sky coverage. I want to explain you briefly the telescope. It's a very simple on-axis design telescope. Mostly we are worried about stray light coming from the Earth. So most of what you see is buffling to remove stray light coming from other sources than the target star. The whole instrument is 60 kilograms in mass and 1.3 meters in length. And we have one CCD detector that will take the images of stars. The whole thing sits on a very small platform from Airbus. And on the left you see the computer model, and on the right you see the real thing in the electromagnetic compatibility test chamber. So we have a special sun shield designed to shade us from the sun. We have special attitude control system that keeps us rotating away from the Earth with our radiators that cool the detectors. And we, being a small mission, we have a relatively moderate data volume of 1 gigabit per day that we can transfer to the ground. Also, we are going into a low Earth orbit. That's not the best for photometry because the Earth is very bright. It's reflecting especially the clouds and the ice reflect the sunlight. So you do not want to look close above the bright illuminated Earth. That's why we're flying over the dawn-dusk terminator and try to look over the dark side, over the night side of the Earth. This works well in April and in September, but since we are tilted and have seasons, it does not work so well in the summer and in the winter, so sometimes we have to look close to the illuminated Earth, and that's where the stray light retention comes in. From an observation concept, we are a follow-up mission, so we look at one target at a time. We can observe roughly 2/3 of the sky, depending on the time of the year. We generate a bunch of observation requests for our own science team, for the guest observers, and for the calibration observation. And then an automatic scheduling tool tries to optimize the ordering sequence of when to look at which target. And every week we re-upload the next sequence of observations. Our ground station is in Madrid, where the data is coming about 2 to 3 times per day, downlinked to Torrejon ground station. Then it's going to the archives and the Science Operations Center, where it's processed and pushed to the archive. And then every week we make one new sequence of observations and uplink it to the spacecraft. Just to get a feeling what the data will look like, similar to Kepler, in the end what we want to have is light curves, but we do not want to download light curves, we want to download images and do the processing on the ground as much as possible. So a typical star field is shown on the bottom. It's a 1 megapixel image, but we're only interested in one star, so we usually cut out this star, we stack it so we get 1 image per minute, and then we download this 1 image per minute to the ground. We compress it, of course, as much as we can, and we also take some additional data like temperatures, voltages, everything that's relevant for the data analysis at a higher cadence. Everything needed to be calibrated, of course, so here's a thermal vacuum chamber we have in Bern. We put the instrument. It has a large window of high optical quality to get in the light, so we have to simulate a star. You know, the stars are infinitely far away, but of course our laboratory is not infinitely large, so you have to simulate a infinitely far away light source with optics, and you want to have a super stable light source to verify the stability of your system. And also you characterize the shape of a star. How does a star look like on the detector? How sensitive are you to temperature variations, voltage variations, and are there any bad pixels on your detector? How do the pixels behave? All this was done, and we were very happy with the results. First of all, we also checked the stability of this optical system, so it's a carbon fiber structure, it's very stable, and also the telescope temperature could be stabilized to 1 Kelvin and the CCD to 2 millikelvins. So by analysis, we are very good in terms of stability. We tried to get an end-to-end 20 ppm measurement with a super stable source. This we couldn't do, but by decorrelation, we estimate we reached about 20 ppm over 6 hours. By analysis, we should be much better, but we couldn't measure better than 20 ppm in the lab. We also did lots of simulations. On the right is one image. There will be then 10,000 of these images. Then you do the analysis. You count the light in the image, and you make a light curve like on the left. And the bright blue dots are simulated Cheops data, and the dark blue are test data. So you can see two things here. Since Cheops is bigger than TESS, we have better signal to noise. But since TESS has a better orbit than Cheops, it has better continuous coverage, and we will have gaps in our data. So it's both good and bad, I would say, but it depends a lot on the target, on location, on the sky, how much interruptions we have. We also did outreach with children. We collected 3,000 children drawings all over Europe and engraved them. We want to get the young generation involved in space science. Engraved them on titanium plates. And mounted them on the spacecraft to fly. And you wouldn't believe how difficult it is to put a titanium picture on a spacecraft, but we did it. So they will now be flying, and we had very good feedback from this, the pupils. They were very excited about this, and we had a big event where we randomly selected 3 children to jump too fast, who could go and see the final satellite and the final pictures. Here, let's just finish up showing you the simulated sky where we will do the observations, the simulation of the first year. The ecliptic is our golden spot. Unfortunately, on the top, or synergy-wise, it's maybe not so unfortunate. We cannot observe the James Webb Continuous Viewing Zone. We can also not observe the Kepler primary field. That's a pity. But we can observe all the K2 fields and redo TTVs there and maybe improve signal to noise. Even so, for faint targets, there's not much chance we will beat Kepler since it has a bigger mirror. Ready for launch. We want to launch hopefully on the 17th of December. This was the last test in Madrid before the thing was packaged for shipping. No problems foreseen from our side, and it was transported in an Antonov to Kourou, where it will launch as a secondary passenger on a Soyuz frigate. And this is a picture courtesy of Airbus, where they have it ready in the clean room at Kourou with the Airbus and ESA teams ready for the picture. Yeah, just one slide, what's going to be after launch. We will do 2 months of checkout testing, which we call in-orbit commissioning. And then the consortium will take over, and we will have guaranteed time observations and guest observer science visits, and what we call monitoring characterization, so calibration images scheduled automatically, and the GTO and the GEO will be 80-20 time allocation. Yeah, and that's my last slide, so stay tuned for the launch in December, and then we hope to have first performance results probably in February on our first commissioning data. Thank you for your attention.
Thank you very much. Thank you very much. I hope that this was really an inspiring insight into what Europe has been doing in the past few years after the huge successes from Kepler in the United States, which also included lots of European researchers. Now we jump into the future. We assume some things will stay with us, like the execution of the Plato space mission, which is going to be represented by Szilárd Csizmadia from Berlin. Please, the floor is yours.
Thank you very much. Yes. So I will talk about Corot to Plato on the behalf of the PI of Plato, which is Heike Rauer. And Corot is a past mission, Plato is a future mission. Actually, astronomers like the abbreviations, so you can resolve these abbreviations here. And many managers, working group leaders, and workers on Plato started in the Corot era, and they were co-eyes of Corot, so there is a logical continuation in Europe that we started with Corot and we continue with Plato. Actually, every children dream about space travel, stars, planets, aliens. I did as well. So it is very nice that at least in Hungary, in the core curriculum for secondary schools, which is valid since 2016, it is stated that astronomy, thanks to the quick evolution of observing techniques, became the leading scientific field of 21st century. These are nice words. The only problem that unfortunately students do not learn anything such in the schools in reality yet. Hopefully this will be changed. But we try to give this dream, at least partly, at least to discover the planets. And if you look the list of the astronomical or astrophysical Nobel Prizes, then you can see that in the 20th century, only 5% of them went to astronomy and astrophysics. But already 33rd of the Nobel Prizes in physics in this 21st century went to, in some way or other, to astronomy. And maybe this somehow reflects what Professor Jack Lissauer said at the end of his talk, that maybe the Nobel Committee in physics think that astronomy and astrophysics can help to solve the problems of Earth. But how? I think this is the way that all these discoveries can change our common thinking, or the thinking of the societies, that how Earth is unique. And maybe we can send a message that we did not find planet B yet, but even if we find it, as Jack said, it is quite hard to reach it. And it just would mean that we export the problems of one planet to another instead of solving them. So this is some motivation to find exoplanets, because it is really has a philosophical consequence and the consequence of the common thinking on societies. The current questions of exoplanetology were summarized by Jean Schneider in 2017. So the first one is to find the planetary properties. What are the interiors, what we can find on the surfaces, what atmospheres the planets can have, if they have rings or evaporation properties. We are interested in the planet interactions with stars, the collisions of planets with comets, asteroids, and other planets. We are very interested in the global statistics. This was the primary goal of Kepler, actually. Average number of different types of planets per star, depending on the stellar properties. And of course, the last and most important question is the astrobiological properties of planets. What kind of life, if any, they harbor, and maybe their moons can harbor life. What are the bioindicators at all? And if we can identify what kind of atmospheric or other molecule can indicate the presence of life there, then how can we detect them? So a lot of theoretical work is needed before we go to the telescope. So these are the exoplanet space missions, plus some ground-based observatories, which looks important for exoplanet science. So the European site started with CORO in 2006, which finished its operation in 2013, and the next one from Europe will be the CALPS, what we just heard, how it will operate, and the next one will be Plato, and it will be followed by Ariel, which is not in this American slide, actually. We must go to the space. It was very well summarized why. I would like to add a few more points to the previous two talks, why we have to go to space to detect exoplanets. First, from the ground, we can detect only the large exoplanets. The atmospheric noise, which is caused by seeing and absorption, really limit our capability to detect exoplanets. A 15 centimeter space telescope corresponds to a 2-meter ground-based telescopes in photometric performance. We don't have the day-night interruption in the observations, and we don't have to share actually the telescope time with others to get enough photometric data points. Of course, there are disadvantages: the price, the satellite rotation, the instrumental effects, the strong systematics, which needs a lot of improvement in any kind of signal processing, but still we can detect the smallest planets only from space. This is just a comparison table of the different space telescopes. And this figure shows the evolution of the photometric precision during the age. Astronomy started with the naked eye, which has about 10% photometric precision, and using photography, photoelectric tubes, and later the electronic devices, the CCDs, we reached such a precision which was just a dream 50 years ago, when the first proposal was done to find exoplanets by transits. And now we can do this. First, the Canadian satellite MOST did it in 2003. Now CORO, Kepler, CALPS, and in the future Plato will do this very good photometric precision. So CORO, the first European planet finder in space, and actually it was the first planet finder in space, had only 4 CCDs, and actually it had a 3 times smaller mirror than Kepler had. So this is why it discovered less number of transiting exoplanets. Its main result is that it opened a door for exoplanet discoveries because it made the first exoplanet discovery from space. Before Corot, only 21 transiting exoplanets were known. All of them were discovered from ground. And only Corot alone discovered 37, so it showed the improvement what we can reach from space. The biggest discovery of Corot probably was the first super-Earth with measured radius. This kind of planets are larger than Earth in mass and radius, but not so much. This maximum 2 times bigger in radius than Earth and 10 times bigger in mass. So this is a planet very similar to Kepler 10b. It orbits its host star only by 20 hours. Actually, the shortest period known planet around the normal star is a Kepler discovery K2137b, which has only a 4.3 hours orbital period, and I was part of the discoverers. And the signal what you have to find is on the upper panel is really affected by the stellar noise. If you remove this long-term variability, you can get the middle panel where the stellar variability is removed, and if you average every orbital cycle of the planet, then you can get the lower panel, a very tiny signal of a transiting planet, which is actually very hot because it is very close to its host star. So its surface temperature in the substellar point is estimated to 2,700 Kelvin, which means that all the rocky material is melted. So Corot 7b looks like on the left panel, according to the artist's conceptions, quite similar to the Mustafar planet, which is George Lucas' conception, actually. So Kepler was mentioned very detailed. It was a 3 times bigger telescope with a more fortunate orbit. And the main results were summarized 2 talks before. I just would like to call your attention on this figure, which is encircled by a red circle, which is the orbital period. For the Earth, it is 1 year around the Sun, so it is 365 days. And the size relative to the Earth, Kepler detected a few candidates there, but they are orbiting faint stars, so it is quite hard to measure the mass of them with radial velocities. The goal of Plato, which is one of the next European missions, is to find planets here. Plato won't find hundreds of planets here. We will be happy if we find 20, 30 planets in this regime, but we target much brighter stars than Kepler did, about 5 magnitude brighter stars, which means that we can measure the masses of these objects. It is not warranted that planet B will be found, but there is a high chance for that. So coming back to Kepler 90, one of its interesting systems is this one. It consists of 7 planets, and one more was found by Andrew Vanderberg in a collaboration with the Google company. And this is among the most populated transiting exoplanetary systems. For example, TRAPPIST-1 has 7 planets. This system has also 7 planets around the host star. And the longest period, you can see the transit light curves of each planet. The longest period planet in this system, planet H, has an orbital period of 11 months. This means that all the 7 planets are inside the Earth orbit if you try to compare this system with Earth. So this is the system, and this sends you another message. In the lower panel, you can see the rocky planets in green, the ice giants with blue, and the gas giants with red. And all the Kepler systems are quite different from our solar system. The uppermost line shows the architecture of the solar system, rocky planets inside, gas and ice giants outside. And only Kepler 90 has a similar architecture to our solar system. All other planets have a quite different one. So the solar system, like planetary systems are rare, and we don't know actually how rare, but not only Earth is rare, our solar system is rare, just we don't know how rare. This is an example from the ongoing TESS mission. I would not like to talk too much about TESS, which is an American mission, but it is the ongoing planetary mission to find exoplanets up to 27 days. And this is quite, I just would like to show this figure. Here we have almost 700 planets which have measured mass and radius, and I plotted them, and the green line is the so-called habitable zone. The habitable zone means in astronomy only that there is a possibility to have liquid water on the surface. So the stellar properties and the planetary properties, planetary orbit allows this. And you can see that how small number of planets can be found in this green region. The life, as we know here in Earth, can exist only in this green region. Maybe there are other life forms, but we don't talk about them because we don't know how to detect them. There are practically no planets here, or they are very close to the lower end of this green region. So with Plato, we try to address a much longer orbital periods. On the x-axis, you can find the semi-major axis of the planet. One corresponds to the Earth-Sun distance, and the stellar mass in solar units. So one corresponds to the mass of the Sun, and the green region is also the so-called astronomical habitable zone. The blue region is the ongoing TESS and the finished K2 and the future KELPS mission. So they really, they can find habitable planets around small stars, but not around solar-like stars, and quite unlikely that they will do this on a regular basis. So Plato's goal is to extend the range of investigation to larger orbital distances. How to do that? With the transit method, which is illustrated on the left panel, and to use ground-based telescope to measure the mass, using the radial velocity method, and using the advantage of astroseismology and Gaia. Astroseismology means that the stars are pulsating, they are never stable, and this can be used to measure the density of the mean star, and combining with this the Gaia astrometric mixture results, we can get the stellar mass. This is a very interesting figure. It shows the whole sky, and the red points, what you can find, for example, here or here, are the so-called Corot fields. You can see that how small they are relative to the whole sky region. This was the Kepler field. It is much bigger, but it is still a tiny portion of the whole sky. The green ones are the successor of Kepler. The Kepler mission was used to measure some other fields around the ecliptic after its primary mission was done due to some failure in the gyroscopic wheels. And Plato's goal are in gray and in blue. So it would observe two fields for 2.53 years and the other fields for shorter time. It targets very bright stars. And actually there will be 24 small cameras. Each of them are just 12 centimeters in diameter. So the total collecting area is about half of the Kepler mission, or even less, but it will observe about 100 times brighter stars, and therefore it can collect about the same. It can collect about the same amount of light on a brighter star than Kepler did on a fainter star. So the signal to noise ratio will be about the same. It will contain 104 CCD cameras. Actually, it will correspond to 2.1 gigapixel resolution, which is about 130 very good DSLR camera, which is commonly used here in Earth. Yeah, this is just a Kepler example. Kepler 37b is a smaller transit signal. It is just 22 ppm than Earth would produce around Sun. As Jack mentioned, this is about an 80 ppm signal. Such small signals were already detected by Kepler. The Kepler 37c shown its transit signal on the middle panel has 90 ppm transit depth. The only big difference between Kepler-37c and what we want to detect is the orbital period. Kepler-37c makes a transit in every 3 weeks, which means that practically we have more than 12 transits per year. And if we want to detect Earth around the Sun, then we have only one. In a fortunate case, we have 2 transits per year. This means that we will have a little bit larger signal to noise ratio, which makes a lot of challenges which have to be solved in the planet detection and characterization. Yes, so some words what can happen after Plato, because Plato does not solve all these questions what I summarized at the beginning of the talk. It does not measure the whole sky, it will measure about 40% of the sky. It does not measure the faint end of the stellar brightnesses, it concentrates onto bright stars. And of course, it is a planet detection and characterization mission, but it does not study the atmosphere of the planets. The planetary atmosphere studies will be done by Ariel, and the next talk will be about this. There are astrometric missions. The James Webb can come in 2021. And all later, we'll have a question mark. There are many ideas what to do. For example, this LUVAR idea, which is an 8 to 15 meter class space telescope. It could collect so much light that it could contribute to the answer to many questions, but this cannot be launched before 2038, and maybe this is an optimistic estimate. There are other missions proposed, like the Earth Finder, which is a radial velocity mission, to targeting 1 centimeter per second radial velocity amplitude. We could see in a figure in the previous talk that 10 centimeter per second can be done from ground with the espresso, which started to operate only this year or last year. There are other ideas to have mid-infrared spectroscopy and spectropolarimetry of rocky planets in the habitable zone. This needs a new satellite, but it would allow to study the surface properties and also the spectral lines caused by different kind of bioindicators and molecules in the planetary atmospheres. So maybe this is the good way when Plato and TESS and other missions will provide the targets, then Ariel and other mid-infrared spectroscopic missions can study the atmosphere. So this is the logical next step. And now we have a list what to find, and at the end we can answer all of these questions summarized at the beginning, but it is questionable that this can be done in 2015 or only after that. Thank you very much.
Thank you very much. And of the talks, the last one is coming, which is Professor Giovanna Tinetti from the UK about yes, thank you. That's done. That's the previous one. Okay, we are done. Thank you. All right. My phone, the smartphone when it is too smart. Slideshow. Professor Tinetti, the floor is yours.
Thank you very much. Ladies and gentlemen, good morning. It's a great pleasure for me to be here today, and a great honor. And I would like to thank the organizer for giving me this opportunity to talk today. Just reminding you, like the other speaker said, that before the 90s, the only planets we knew were the one, our own sun, in the solar system. And Pluto back then was still considered a planet. Then we lost to Pluto in 2006, but at the same time, what we learned in the past couple of decades is that planets are really ubiquitous in our galaxy. And statistically speaking, out of all the statistics of all these techniques that we're using today to find new planets, we have the strong evidence that there are as many planets as stars out there in our galaxy. So we're expecting really billions of planets in our Milky Way, which is fantastic. You're already seeing from our speakers the fact that the counting at the moment is going up to over 4,000. These are the confirmed planets. And again, as pointed out by our speakers, it's not just the number of planets that we are finding out that is quite incredible in such a short time, but it's also the fact that there are many planetary systems, and we start to have even some exomoon candidates, which again is quite mind-blowing. Other speaker pointed out that what we are seeing out there is sort of a cutting edge between science and science fiction. And I also think it's worth mentioning that sometimes the truth that we're seeing is really stranger than fiction. And in particular, I'm using in the definition of Jack Lissauer, science fiction, this is soft, probably science fiction, coming out of Interstellar. It's certainly not true that we can go on these planets, we cannot travel there, but what is probably true that we see many objects out there that are compatible with, at least the density is compatible with having some motion at the surface, what we call waterworlds. And the previous speaker already mentioned the fact that we have many lava planets. So in particular, it was mentioned Corot 7, B, but also Kepler 10b. These are all planets that are orbiting so close to the star that the temperature at the surface goes up to 2000 degrees Celsius, even more. And at those temperatures, rocks are really molten. And so that's why we're thinking of these objects as lava planets. And so that's why, again, the science fiction image is quite accurate. Also, another technique that hasn't been mentioned today, simply because we're all more focusing on space missions, microlensing. That is delivering a lot of planets, in particular small planets quite far away from the star. And so again, we speculate that at those distances to the star, the planets are quite cold. And so again, this image coming out of Interstellar is probably quite accurate to sort of portray how this small and cold world might look like. And finally, again, Kepler, a fantastic mission, as we heard before, we discovered many planets around binary stars. And so before Kepler, we didn't necessarily could bet on the fact that a binary star could have planets, but it seems to be the case. And so as you can imagine, these are probably very exotic words because you have two sunsets, two dawns, and so on and so forth. So something that is hard to picture. Again, just to emphasize what has already been pointed out by the previous speaker, that the NASA Kepler mission has been absolutely revolutionary. And before Kepler, we had absolutely no idea what was the statistic of planets out there. And I think the fact that now we know, thanks to Kepler in particular, that the most common planets out there are objects that are in between the size of the Earth and the size of Neptune, objects that we call, in a certain sense, to hide our ignorance, super-Earth or sub-Neptune. We don't know exactly what these objects are, but fabulous. And the question then is why we don't have a super-Earth in our own solar system. And so clearly, all this discovery really started to point out our ignorance of planets in our own galaxy. And so for the next decades, we have all this long series of questions that we really want to try to address. We want to understand why the solar system is as it is, because as the previous speaker mentioned, solar system seems not to be the paradigm of planetary system of our galaxy. And so all of a sudden, as astrophysicists, we need to explain why. And so where this diversity is coming from, we believe qualitatively that it must come from how planets are forming and evolving in our galaxy, but again, this is a qualitative statement. We need to know how exactly that is happening to understand why in the end the solar system is as it is. And of course, we're interested in many other questions, including whether some of these planets are habitable or not. So what do we know today about all these planets? So most of the time, if the transit technique was used to discover them, we know how big these planets they are. We know their size. Most of the time, we also have some extra measurement using another technique, radial velocity in particular, or other techniques to constrain the mass of the planet, so we know how much these planets are weighing. And so if you know the size and the mass, then you can look at complex diagram like this one, where basically we try to see whether we can match the density of the planet that you can calculate out of these two numbers with models of the interior that gives you the composition of the planet, whether it's more gaseous, like Jupiter or Saturn, or on the contrary, is more rocky like the Earth, or somewhere in between. And of course, what we're seeing is that this diagram, or telling us that things are very complex. It's very complex with just one information, one parameter, the density, to really work out what's going on there. For instance, human beings have a density that is very similar to salty water, but human beings cannot necessarily be described as salty water. We are much more complex, and so we clearly need to know more. What we certainly know also is the distance between the planet and the star, and so out of that we can estimate the temperature. But again, also the temperature can change depending whether the planet has an atmosphere or not, and what is the composition of the atmosphere. So bottom line, this is all great, but we want to know more. So you heard by other speakers of the transit technique, and what you're seeing here is the transit of Venus. I'm afraid we don't yet have an image beautiful like this for an exosolar planet, but the technique is the same. And it's great to discover the planet, but you can do more. Basically, you can focus on the very thin layer that is enveloping the planet, what we call atmosphere, that is made of gas. And given that it's made of gas, the gas can be transparent in certain frequencies of light or more opaque. And so what we can do is to measure basically how the light of the star is filtered through the atmosphere of the planet and see what kind of molecules are present in that atmosphere, or there are clouds, what's going on, because we can see how the light from the star is absorbed or reflected or emitted by the gas that is present in the atmosphere. And it looks like science fiction because, as you can imagine, doing this kind of measurements for planets that are tens or 100 light years away, it is difficult. You heard a lot about part per million. Here, if you want to be part of this game, you need at least to aim at 10 or 100 part per million, otherwise you don't even are part of the game. And what is, I think, even more extraordinary is that we're already able to do this with current instrumentation, in particular from space. I think it's extraordinary because missions like the NASA Spitzer space telescopes or the Hubble space telescopes, honestly, were absolutely not made for doing this kind of high precision measurements. But they're coping very well, and the entire community has worked very hard to make sure that we understand a little bit better how these instruments are working and try to, in a certain sense, provide some mitigation to the systematic that, of course, are there. And I think as of today, for at least 40 giant planets, so big planet, typically more gaseous one, we know that typically water vapor is present in those atmospheres. Of course, the main component is hydrogen, but then on top of that, we're seeing a lot of water vapor, we're seeing a lot of clouds. In a certain sense, it's not unexpected, also because, unfortunately, the kind of window that we can look at with current mission is relatively narrow. And so in those frequencies that, in particular, Hubble can deliver, we can see mainly water vapor and clouds and little more. But of course, this tells us these techniques are really working very well. And of course, it's not giant planets that are being observed. The TRAPPIST system was already mentioned before. Fantastic discovery, 7 planets, more or less the size of the Earth, or around an ultra-cool star that is much smaller and colder than our own sun. And of course, we want to know more about the atmosphere as well, and there were some measurements that were taken with Hubble. Unfortunately, these planets are very small, probably very cold. If they have an atmosphere, it's probably quite compact, so it's not compatible with what we can do with current telescopes, so it's more for the future, and so that's why you're seeing this sort of flat signal. But again, the fact that we can even point at those planets and start to characterize those planets, I think, is wonderful. And if you're really interested in habitable zone, we already have at least one example that is coming out of Kepler, is the planet K218b, for which some measurements were obtained through the Hubble Space Telescope. And my team at UCL and also another team in Montreal, we work out that actually the signal out of the telescope is compatible with the presence of water vapor in the atmosphere of this particular planet. Now, this is one of those planets that we don't know exactly how to classify. It's a super Earth. What exactly is these objects? Because it's a few times the mass of the Earth, and we know there is still some hydrogen in the atmosphere. But again, the very fact that we can look at small planets today in the habitable zone of the star and at least extract some information of the atmosphere, I think is quite mind-blowing given our instrumentation. And so, of course, the future will be better, and you've seen this slide already before. In terms of atmospheric characterization, not just detecting new planets, of course, we're all waiting for the James Webb Space Telescope that will be launched in 2021. 6.5 meter of telescope in space, biggest telescope ever been built. Very sensitive detectors in the infrared. It means that you can look very carefully, in particular, at small planets in the habitable zone of these relatively cool stars, like the K218b, like the TRAPPIST-1, and I'm sure that a lot of the telescope time will be given to look at those objects. But of course, we want to go also for the large statistic. So not just cherry picking some of the best atmosphere that we can look at out of these planets. We want to have the big picture. And because of that, we proposed to the European Space Agency a few years ago a mission called Ariel. And Ariel has been selected last year to be the next medium-sized mission to be launched by ESA in 2028. So what is Ariel? We're talking about a 1-meter class telescope that will be launched in L2, so same orbit of James Webb. So as you can see here, I will be launching at 1.5 million kilometers away from the Earth. And L2 is a very stable environment, so if you want to do measurements in the infrared, is where you want to be. And also from that point, we can very efficiently look at many planets because we want to be able to look at the atmosphere of about 1,000 exosolar planets. We will do spectroscopy, so really looking at the light that is emitted or absorbed by all these atmospheres from the visible down to the infrared, which is where most molecules are really absorbing. So we want to know the chemical components of this faraway atmosphere. We want to know what is the temperature, where are there clouds, what is the weather, what is the climate of all these planets. And at the moment, the payload consortium is including 17 ESA countries. You see all the flags here. There is a very strong contribution from Hungary, from the science in particular, Concoli Observatory, but also on the hardware part. And NASA participation, I'm really pleased to say that it was confirmed last week. So now we have a formal NASA participation delivered by the CASE team. So these are just a couple of examples of the kind of spectra that we will be able to measure with Ariel, with big planets, small planets, different temperature, different stars. The idea is to really provide a galactic statistics of the composition of all these atmospheres. This is just a snapshot of the Ariel team that is increasing. So we're very pleased to see many new people joining our mission. We're also working quite a lot, not just among the astrophysical scientist community, but also with the public. And in particular, we launched this year an Ariel Data Challenge that was extremely successful. The challenge was about asking the astrophysical, but also machine learning community, both professional but also amateur, to help us basically to reduce some of the systematic that can be created by stellar activity. And the response was huge. We had over 100 teams that participated all over the world. The first two were awarded at the European Conference on Machine Learning, and the first 5 are now publishing a new publication. Among them, there is a 17-year-old from Canada that is a spectacular work. So we hope to do even more data challenges given a success in the future to make sure that everybody's participating to the preparation of the mission. And in fact, also we're asking the help of amateur astronomers to help us defining much better the ephemerides of the planet, so when exactly the transit is occurring to make sure that the mission is more efficient. And again, the Exoclock initiative is another initiative that is getting a lot of response from the public. And so you can just log into the website, point out where you are in the world, when you want to do your observation or what kind of telescope you have, and you will have a list of priorities or targets that you can observe to help us out of the Ariel catalog. Before I wrap up to conclusion, I just want also to point out that there are new initiatives also from New Space. We all heard about New Space, the fact that there are more and more small satellites that are being launched through private companies for telecom and also Earth observations. And also for science, astrophysical science, I think we can get advantage of that. And in particular in the UK, we have this initiative that is led by Blue Sky Space, that is a private company. And we are building Twinkle, that is a small satellite in all orbits, able to do spectroscopy, both in visible and infrared. And we're working with Airbus and ABB. And the idea is to launch this small satellite, about 45 centimeter telescope, in 2023. And Twinkle will be able to do a lot of astrophysical science, in particular exoplanet, spectroscopy and follow-up photometry, but also solar system type of science. And so more and more data will be available to the community. I believe my time is over, so let me wrap up to conclusions here. Exoplanet appears to be ubiquitous in our galaxy, is fantastic, mind-blowing, means that all of us working in this field will always be employed. The number of discovered exoplanets is increasing, exponentially increasing, and there are even more missions coming that will deliver more and even better planets in the future. We still don't know very much about those planets, and that's why we really need to make sure that we have new data in the future, and in particular for the atmospheric composition to understand better the chemistry, the climate and the weather of this planet. Having satellites like James Webb or even the small Twinkle happening in the next few years is fantastic. And in particular, having a dedicated mission like Ariel gives us the first opportunity to go for the large statistical sample and therefore get the big picture out of the galaxy. I will iterate the message that also Jack gave before. We can't go there in this planet, and I use a cartoon that came out in the UK when K218b came out. I think it's really useful to stress everybody that we really can't go there, and we absolutely need to take a good care of this one because that's the only one we have. Thank you very much.
Thank you very much. I would like to ask the speakers to sit back. We have still 10 minutes, I would say, for discussion, questions. I just got the funding decisions from OTKA, so who are interested, Peter, congratulations. You got it. And Zsolt Kővári, are you here? Vera Dobos, you got it. So congratulations. It's a CHEOPS related, or Exoplanet postdoctoral fellowship. Let's congratulate the young lady back there. Just got the funding decision. the very latest postdoctoral fellow in Hungary in exoplanet science. So, I don't know what to do with this opportunity. As I fully understand Jack's concerns that organizing meetings and flying and giving huge carbon footprints, but then we are humans. And the human nature includes interactions with other humans. And my increasingly stronger and stronger feeling is that through videocons, it doesn't work like that. I mean, I need you to be here to feel your feelings. So I think human interactions require human presence, at least for within the foreseeable future. That won't change until we go into a transcendent phase of post-human beings, which may happen by 2050. So I would ask for the audience, is there any comment or question which could be answered by the highly esteemed guests of this thematic session? Anyone willing to address what has been said or what has been left out of the discussion? Everyone is just, yep, oh, this is still Giovanna's time. Jack, you may have some comments to start with. We can start with you, yeah.
I agree with Laszlo that we need international travel for meetings. I'm not suggesting we eliminate travel. I'm suggesting that we do it, we look carefully at travel, and if we have a committee and it's meeting for a day, then we do that by telecom. If we're bringing speakers in to give seminars at our institutions, we find other institutions in the area where they can also speak. So if few speakers can come and give talks at several places. You'll get as many talks from distance. It just requires some work, but we do need it. Personal interaction is very important for science. It's an international discipline, and we don't want to eliminate it.
Yeah, thank you. Anything from the other speakers to comment on? I would like just to raise one question, which was also discussed during the workshop at the Concoli Observatory. What would you think will be the next Nobel Prize winning discovery from the exoplanet field? So I don't want to nominate people, but topics. If you just have 10 seconds of thinking from the speakers, what do you think will be the next Nobel Prize winning discovery in the field of exoplanets by, let's say, 2050? Anyone wanting to start with? Jack.
Well, I think it's going to be something to do with habitability. If it's SETI, getting a signal, radio signal from some intelligent form of life, that's wonderful. Or if it's a biomarker, an indication that there are different gases that couldn't exist in equilibrium with each other, or which are produced by a technological civilization. For instance, if you saw chlorofluorocarbons in an atmosphere, you would say that that planet has a species which is intelligent, but maybe not that wise.
All right. Any of you, Joanna or Chris?
Yeah, I mean, I can just follow what was been said. I also think now, I mean, the first prize is always the easiest. You get it by detecting something, but once it has been detected, you have to go a step further and really learn something fundamentally new.
Mm-hmm.
And this, I think, at least my personal drive is how special is our Earth in the universe. I mean, are there other habitable planets out there, and has the genesis of life taken place elsewhere? So, in this sense, if you can indirectly, or if you get very lucky, directly with SETI or similar, that you actually detect intelligent life, I mean, detecting biological activity would certainly be a candidate.
Mm-hmm. Yeah. Szilárd?
Astronomy is an instrument-driven science, and all instruments which are planned for the next 1-2 decades are oriented to find life outside the solar system. So I can agree with the previous two speakers. Quite probably the detection of any good bioindicator is a very good candidate for the next Nobel Prize in exoplanet.
And Giovanna, will Ariel be capable of doing that?
No. No, I think Ariel doesn't have a sweet spot, the habitable zone. I think that is more James Webb. If we want to put some bets and look in a habitable zone planets, I think James Webb, in particular, habitable zone planets around the Pole Star, I think that's where James Webb might be deliver some good indication. But I would like to put my bets on something surprising coming out of exoplanet, simply because I think as a field it has been quite an idea and sometimes serendipity-driven field. And so I like to think that not all is figured out, although we have all these fantastic missions well aligned. I like to think that somebody will come up with some new idea, or maybe just using some of the data that will be available and will surprise the rest of the community. So that's where I would like to see things happening.
Thank you. This is really inspiring thought. Any other comment or suggestion, or just, because the opening window or the window for commenting is just about to close, so we have now the lunch break for the World Science Forum. I really hope that all those who came to listen to our guests, who are really representing a very, very focused field in astronomy and within astronomy exoplanet research, that they gave us a picture, which is, I think, there is more reason for optimism than sort of, I think that the main message is a positive one. Yes, there is no planet B, there is no plan B for humanity, that's for sure. And astronomy will always be a 1% contribution or 1% spending, or less than 1% spending in science, but still I think that's something, being a human, or really being a human person or human being includes those moments when we just look up and think about what's out there. Without that, we are just, that regular daily life, the gray daily life, we need to escape from time to time. And astronomy gives us a very excellent and exciting instrument to really go out and look up what's out there. So with these words, if Jack maybe...
That I agree with Giovanna, that it's more likely to be something that we don't know about. It's just among individual things, my guess would be life, but that's not 50%. Something else is most of the chance.
If the UFOs will visit us next year, then who cares whether we can find spectroscopic signatures of bio-related biosignatures. Who cares? UFOs are here. So, yeah. All right. Thank you very much for the guests. Let's thank the speakers again. And I really thank the audience, and please enjoy your lunch.